Hi friends, in this video we will learn about input output instructions. So in the previous videos we have seen what is a basic instruction cycle, what are memory reference instructions, what are register reference instructions, here input output instructions, and what is a program interrupt. In the first case, so this is the block diagram of input output configuration. What does input output configuration has? Basically it has two terminals for input and for output, and two registers, input register and output register, one accumulator and serial communication device. So let's look here. Keyboard is my input terminal, transmitter interface and receiver interface are my serial communication devices. Printer is my output, so this is my input, this is my output, these are my serial communication device. This is input register, this is output register, and this is accumulator. And I have two flags here, interrupt flag, or input interrupt flag, output flag. These both are controlled flip-flops. Okay. Now, my serial information which is to be sent is stored in input register from keyboard. My serial information which is to be printed by the printer will be stored in output register. These input and output registers will act serially with communication devices, whereas accumulator acts parallelly with the communication devices. Okay. Now, every instruction has 8 alphanumeric codes, 8 alphanumeric bits, right? So, whenever now my instructions, my input output instruction is completely based on these two flip-flops. Okay. So, whenever my FGI input flag is 0, it says that instruction from the keyboard is transferred to input and computer has accepted the input. Whenever it is 1, then it says that input register has some new information to take or to accept the new information. From there, I will send my input instruction to accumulator. From accumulator, it is transferred to output register parallelly. Okay, so here FGO is equal to 1 indicates that whatever the instruction is there, it is sent to output register parallelly, and automatically this flip-flop will be set to 0 once it receives the information from accumulator. Then again, this output register sends the data instruction to the printer, and whenever the printer completes its execution, it is again set to 1. Right? Now, whenever this is the input register is performing one instruction, okay, so it does not allow any other instruction to interrupt this. That means whenever the instruction is going on here, and if you stuck a key on the keyboard, the information in the input register does not change unless and until the complete information in input register is accepted by the accumulator. Similarly, the same is the case with the output register. Unless and until it executes the given instruction or it prints the given instruction, it does not allow or does not read the next instruction which is coming from the accumulator. This is how input output configuration is made, and we have some instructions for input output configuration. from B6 to B11 we have 6 type of input output instructions provided. Okay, this P indicates D7I T3. I already mentioned that this occurs when D7 bit or D7 decoder of the instruction cycle is 1 and my interrupt is 1, and this cycle occurs when in the control timing of T3. So I denote D7I T3 as my P. Then I have 6 instructions. First one is, and instructions is IR 6 to 11. In instruction register, from 6 to 11 bits is my control functions. So 6 to 11 bits are my control inputs. Why I need these control inputs? To generate input output instructions, to check the flag or input outputs, flags, and also to control the interrupts. Right? Now, first one, PB11 is AC07 input register is sent to accumulator 0 to 7 bits and my flag input is set to 0. So this is input character is sent to input register through to accumulator. After sending, I will clear my flag. Similarly, from accumulator to output register, and again I clear my flag. Right? Next, if my FGI is 1, that means what? Whenever my FGI is 1, it is saying that I have new information to continue. So skip that input flag and go to next instruction. Whenever my FGO is 1, it says skip the output flag. That means it is not ready to take the input, just skip that and go to the next instruction. That is, we increment the program counter by 1, where this makes the address to go to next instruction, thereby starting the operation with the next instruction. And next is input enable on. We'll see where input enable is. We are using where input enable is later. Input enable is 1. That enabling input interrupt enable is off. Okay, these are the basic 6 instructions we use in the instruction IO instructions. Next is program interrupt. Right, program interrupt. So whatever procedure we are dealing here is called programmed control transfer. This is all programmed and in a control transfer, right? But this way, doing this way or transferring the information in or out from accumulator in this way will be inefficient. Why? Because suppose consider an input output device which can transfer 10 characters per second, right? That means it transfers 1 character for every 10 power 5 milliseconds, 1 character for every 10 power 5 microseconds. Microseconds. So in between this, every 10 power 5 microseconds, the computer is doing 2 operations. One is checking the flag bits, and the second thing is deciding whether to transfer the instruction or not. Okay, now these 2 operations are done by the computer for every 10 power 5 microseconds. That means 10 power 5 by 5 approximately 50,000 times. That means for every, in between every instruction, it is checking 50,000 times the flag and deciding whether it is to transfer the information or not. This makes the computer to lag in time, or it takes more time for the evaluation of each instruction. Okay, for every instruction cycle we have only one microsecond time, right? So but by doing this we are getting 10 power 5 microseconds, 50,000 microseconds for every instruction to complete. So this is not an efficient way for transferring the input or taking the output from the registers. Instead of this, we have got an alternate procedure for doing this using an interrupt flag. Using interrupt flip-flop. That means whatever might be the input-output device, okay, if it is ready to take, if it is to transfer the information, then it interrupts the computer in middle, asking, I am ready to transfer the information, kindly take the information, okay, so that we do not waste the time, and in the meantime the computer can perform the other productive task which would be helpful and which does not even waste the time of the computer. So I use my input flip-flop, that means interrupt enable. Interrupt enable. Whenever it is 0, whenever this bit is 0, computer cannot be interrupted by the flags. These flags, whichever is there, those cannot be interrupted. Computer cannot be interrupted whenever IN is 0. But whenever IN is 1, then computer is interrupted by the flags. Okay, we'll see how it works. Okay, here R is my flip-flop. Okay, whenever R is 1, it is interrupt cycle, and R is instruction cycle. We already seen what is instruction cycle and how does it perform. Fetching, decoding and execution. Fetching and decoding the instruction, and next is executing the instruction, right? This is my instruction cycle part. But whenever my R is 1, it is interrupt cycle. Okay, we'll see how this interrupt cycle goes. Now, whenever I already mentioned, whenever my IN is 0, then computer is not interrupted, so it executes the current instruction only. But whenever my IN is 1, then it will be checked with the input flag or input control flip-flop. Okay, whenever input flip-flop is 0, it says that input is not ready. That means this flag, input register, is not ready to take the information. Next, whenever this is 0, it checks with the output flag. If it is also 0, it is that both the input and output are not ready to take the information or to give the information. So you execute the same instruction. There is no change in the instruction. But whenever this flag is 1 and this flag is 1, we set R to 1. Right? Whenever these both are 1, we set R to 1. Whenever R is 1, the control is shifted to interrupt cycle. Where interrupt cycle is hardware implementation of BSA. BSA, this is already mentioned in memory reference instructions. BSA, branch and save address. This is the type of instruction we mentioned in memory reference instructions. Okay, this is just an hardware implementation of this one. That means whenever we encounter an interrupt by the computer, okay, then the computer will stop its execution, whatever the instruction is executing there itself, and that memory location or that memory address is stored in first part of the memory. Okay, the first part of the memory m of 0. Okay, then it continues to execute the instruction whichever it should be performing, or it should be executing by the interrupt. Okay, so whenever it is interrupted, it executes the instruction which is interrupted, and after that, after completing that instruction, it again comes back to the previous instruction which it was executing. Okay, that is what shown here. Store return address m of 0 to PC is transferred to m of 0. Now wherever the PC is, that address location is, or that memory location is stored in m of 0. After that, branch to location 1. After completion of this, you directly branch to location 1. After completion of the execution, you make IN to be 0. Why IN to be 0? Because if IN is set to 0, the normal instruction which is to be executed, that will be executed, and R to be 0, so that it performs the instruction cycle as it is. Interrupt cycle is over. After that, it should continue. It should be continuing with the instruction cycle. So these two flags should be set 0, so that it performs the instruction cycle. This is how an interrupt cycle is worked, or program interrupt is worked, and those are the 6 input-output instructions used in the computer. By this, we have completed what is an instruction cycle, what are memory reference instructions, what are register reference instructions, what are IO instructions, and what are program interrupt and interrupt cycle. In this video, we have learned what is interrupt cycle, right? So in the later video, we're gonna learn how to use them all in one computer and make an whole device which is using all these instructions. That's all for this video. Thank you all.